Hi, my name's Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to show you how to superpose two or more proteins that have some reasonable degree of secondary structure similarity but lack sequence similarity. This would be a useful workflow for comparing binding pockets or identifying structurally conserved regions. So let's get started. So I'm just going to start by opening the two files that we're going to be working on today. I'll find those in the sample mol directory, and I'm going to select them both at the same time by holding down Shift on the keyboard, and then I'll just go ahead, select them both, hit OK, and they appear here in the main window. To understand what we have in our system, I'm just going to go ahead, open the System Manager and pin that to the main window as a means to manage the data that we have in our system. From here I can make selections, I can hide and show different atom sets, and I can also render and generate surfaces. And I'll use the rendering tool so that I can render our structures according to their tag, so that we can easily identify them. Now seemingly these two structures appear quite different, but to better understand that I'm going to go ahead and open the sequence editor, and this is what we use to display sequences. We use the main window to display atoms. The sequence editor is also the launching point to the various protein modeling tools that we have in Mo. So here I find our two PDB tags and their corresponding chains. Before I analyze these, I just like to set up the sequence editor as I prefer to see. So currently I have to scroll along to see the entire sequence. I prefer to wrap that, and I'm also going to switch to the single letter amino acid code and scale our sequence slightly. So what I'll do next to understand the real similarity between these two structures is perform a sequence alignment. So I'll hit Align Superpose, which opens this panel at the bottom of the sequence editor. It comprises three main sections, the first being the Setup Chains button, which provides us control for using blocks when we want to perform group-to-group alignments and subunit assignments for multiples. The middle section of this panel is for aligning sequences, and the third section is for structural superposition. So I'm just going to perform an alignment using the defaults. So I'll hit align, the sequence moved, the structures did not. That's because we're just aligning sequence at the moment, not superposing structures. And then I'm going to analyze these by using the dendrogram. So I'll just toggle on my dendrogram, which by default is showing me the similarity. If I hover over a tree, a branch of this dendrogram, it shows me that the similarity between these two structures is only 13%. Now, if I did perform a superposition, I'll do that just for fun here. I get a readout here of 26 angstroms, and if I click on the main window and center in on that view, you see that it didn't work terribly well. However, I spotted that in the sequences we've got a ligand entry for both of our PDB tags, and if I just click to expand on the System Manager, I see that they're both within here also. So that's a clue that perhaps we could align to the pocket residues, which might make a bit more sense. So I'll try to do that here. So I'm going to superpose on the pocket residues, and I'll click superpose, and again it doesn't work terribly well, which gives me a clue that there's probably insufficient similarity in the direct vicinity of the pocket. So I need to think about making a selection beyond the immediate pocket. I can achieve that using the selector that we have in Mo. So I'll just go ahead and open up our selector, which appears here at the top of the main Mo window. So now I can use selection language to select the residues that I'd like to perform the superposition on. So I'd like to perform this operation on each tag separately. So I'm going to start my selection language by typing by tag, which, as I say, will define that we want to perform this operation on each tag separately. Then I need to define what I'd like to select relative to, and that's going to be the pocket. I want to select everything within 10 angstroms, so I'm going to type in 10. And then the thing that I'd actually like to select would be the residues. So I'll go ahead and hit return, and that's selected the residues within 10 angstroms of each pocket separately. You'll notice here that the atoms that have been selected in the main mode window is synchronized to the sequence editor, so they're also selected in the sequence editor. And from here, what we can do is change the type of superposition to perform that superposition on the selected residues. Now, we already know that there's very little sequence similarity between the two structures, so I'm going to perform the superposition on structure only, and then I'll go ahead and hit Superpose. So the structures are now superposed based on the domain motifs of those selected residues, which brings the binding sites closer together. If I just go ahead and select these two again, we can see that by selecting the two nucleotides, they've now been brought together. If I go back to the sequence, you'll notice that big parts of the sequences are not aligned. So you see these dashes here. That's because they're very different in terms of their structures. But many residues from the binding pocket are now aligned. Now that the sequences have been aligned to match that superposition, we can think about improving the superposition even more. So what I'm going to do is select the pocket residues, and I'm going to use the existing alignment now that we align by the structure, and then I'll hit Superpose once more, and that brings our RMSD down again. It's down to 1.766 angstroms, which is quite reasonable. Now, whilst talking about different superpose options, I just want to highlight a couple of options that we have available to us. The first is refine with Gaussian distance weights. That will bias the superposition towards residues which superpose well. And the second is accent secondary structure matches, and that biases the superposition of alpha helices and beta strands to optimize the superposition of those secondary structures. I'm not going to use those today, I just want to make you aware that they exist. So going back to the main mode window, in this final superposition we can see that the ligands are well superposed, as is the secondary structure that surrounds the binding pockets of these two proteins, which are quite dissimilar, but by aligning those proteins by secondary structure we find that similar fold around the nucleotide binding region, as I say, in otherwise quite dissimilar protein structures. And with that, it brings us to the end of today's session, where we superposed a pair of proteins based on a three-dimensional structure only, so we didn't use the sequence information to generate that superposition. This is a useful workflow for comparing binding pockets or identifying structurally conserved regions. I hope you've learned a lot today. If you have any questions, please do reach out to us at support@chemcomp.com.